of active galactic nuclei. So accretion disk and black hole. So there is, depending on the angle that these objects are observed from our perspective, there is a historical classification of objects of Aegeans, although in principle they should be the same kind of objects without counting for this dichotomy in jetted, non-jetted. And actually, in the case of radial out or jetted objects, you can have from going from very large viewing angles of the observer with regard to the jet. You can go from narrow line radio galaxies, broad line radio galaxies, or blazars, which is actually, as I said before, the kind of objects I'm going to talk about. They are those jetted Aegeans that have their jets closely aligned with the observer at less than or about less than actually 10 degrees from the line of sight, and they are also subclassified also in two main kind of objects, which are flat spectrum radio quasars and BL-Lacertae or BL-Lac objects. And this classification actually was mainly made at the beginning based on the different optical spectroscopic properties of both kind of objects. But we have been more information during the latest decades, and we know that they have many other different basic differences between them. There is still a debate why this is happening, or even if this is happening at all. Because many, well, some people claim that this is only a matter of the power of the jet that allows to see spectral lines or not, or any other components in the jet. But this is still an open debate which is not solved. It is not neither the topic of this talk, anyhow. I'm not an expert on that. I just know something. Okay. The relevant emission regions in not only in blazars, actually, but also in active galactic nuclei. We have actually the accretion disk that emit optical to UV thermal emission, and then what it is called the dusty torus that can be understood as an extension of the accretion disk to larger distances that emits mainly infrared thermal emission. It is called it, and actually the inner accretion disk. You also have the broadband region, which is a region where, I mean, it's essentially a clumpy, dusty medium that can be ionized by the powerful emission of the center engine. There is usually what it is called a corona, which is a region around the central engine where emission mainly from the accretion disk can be scattered up to X-rays. And then, of course, the relativistic jets that emits mainly non-thermal emission, both synchrotron and inverse quantum, along all the spectrum from radio to gamma rays. Okay, jet formation. This is one of the big topics regarding both Aegeans and blazar science. For lots of years, we have been debating what was the mechanism for jet formation, and we are now starting to understand a little bit more about that, mainly from numerical simulations and theoretical work. But we still do not have observational confirmation of any of the theories regarding the jet formation mechanism. In any case, we know that the essential ingredients for the formation is the large gravitational potential of the rotating black hole at the center, material from the rotating accretion disk, and of course co-rotating magnetic fields that are later transported to the jet, and so that actually student studying magnetic fields in jets from Aegeans is actually crucial to understand both the jet phenomenon, the properties of the jets, and also the jet formation processes. So that's a good argument, actually, to study these kind of objects in polarization, because polarization observations provide information about the magnetic fields. The scales of jets in Aegeans, after their formation, they are able to extend up to distances that are as large as hundreds of kiloparsecs. And actually, an open issue still is how these jets are able to propagate up to so large distances, taking into account that they have been losing energy in all the way through from the beginning where they were formed up to such a huge distances. So it is thought that there should be some kind of internal acceleration mechanism that we don't understand at all still. People think about acceleration of particles in shock waves, also reconnection mechanism in the internal plasma of the jet, and many other, a few other mechanisms, but this is still not clear. Well, the thing, what I wanted to show in this slide is that besides jets can stand up to very huge distances, the region where I'm going to concentrate in this talk is this one. Is the innermost regions of the jet where the jet has been just formed, or even, or perhaps at most, a couple or a few parsecs away from the central engine, right? These distances, these regions actually can only be imaged. The jet itself can be imaged only with very long baseline interferometry, but we know from other work that the short millimeter emission of these regions, even when observed with VLBI, it is very, very compact. So in principle, observing this kind of objects with single dish telescopes where you are integrating all the emission of this very compact region is a very good first approximation to the properties of these regions. Whenever you cannot use VLBI, a very long baseline interferometry, which is a technique that requires many resources, many telescopes coordinated together, and it's quite difficult to have deep and intense monitoring of this kind of objects with VLBI, right? Okay, what else about Aegean jets, blazer jets in this case? We know actually that actually since many decades, actually since the beginning of the 70s actually, that these sources show proper motions of jet features, as you saw from this one. Actually, I'm going to show it again from this one, that are usually called components that propagate downstream the jet from the innermost regions of the jets. This is what it is usually called the core, and actually this is the jet that shows components propagating. And we know, actually, because we can relate this with numerical simulations, that these features have a lot to do with plasma perturbations that propagate on the jet, that are most often identified with shock waves, or they are sometimes called blobs or knots in the jet. Okay. Main property of relativistic jets is that they are relativistic, of course, and this is not a joke, because the fact that they are relativistic makes them ask to see a distorted view of this kind of objects, and this distortion is more prominent as the jet axis approaches to the line of sight, to our line of sight, and also as the speeds in the jet are closer to the speed of light. And actually, blazer jets has both two ingredients. So relativistic aberrations are very important on the interpretation of the data, because actually what you see is what relativity gives you from the actual objects. So the first, one of the basic things that effects that we see from the jets is that the jet pointing to us often shows apparent superluminal motions as those that we have been I have shown in the previous slide, and it is illustrated here in this collection of in this sequence of very long baseline interferometry images of this very well-known blazar OJ287. So what we saw here is that in a time range of about 1 hour, 1 year, sorry about that, about 1 year, this feature was propagating in the plane of the sky by a distance of about 12 light years. So that means a speed larger than 10 times the speed of light. This is an apparent effect. It's very well understood. So we are not violating the theory of special relativity, but it is something to take into account when you interpret the observations from this kind of objects. It is also thanks to late aberration to relativistic aberration of light propagation, the emission of the jet which points to us from the two that are formed actually from the central engine, it's enhanced, is boosted with regard to the counter jet. So that is the reason why when we observe blazars with very high, ultra high resolution actually, with VLBI, we only see one of the jets and not the counter jet. Actually the jet approaching to us is enhanced, the emission from the jet approaching to us is enhanced by a factor of typically 1,000 to 10,000, and by the same factor is dimmed on the counter jet. So that's usually blazar jets are seen as single jets. And also actually, because of the same effect, actually the emission that we see from relativistic jets is beamed in the direction of propagation of the plasma, and this is one of the reasons why when you see the jets close to, with your line of sight very close to the axis of the jet, then you are able to see, as I said before, enhanced emission in all spectral ranges that favors actually this kind of objects to be observed at high energies where the sensitivities are very, very small still, and that makes these jets to be observed at even at gamma rays, where the technique is still not very well developed for observations of weak objects. So this is the typical spectral energy distribution of blazar jets, essentially from the long wavelength radio domain and to the very high energy gamma rays. So we usually have this double hump. This first one produced by synchrotron emission of the jet, and this second one produced by inverse quantum emission. This is actually one of the main standard models. Inverse quantum emission produced by the upscattering of photon fields either from the jet or external from the jet. There are other alternative models that are still to be tested, like for example synchrotron emission of protons and any other models, but this is still not well established. Well, what I wanted to show in this slide is that this green light, which represents the short millimeter range, which is the one on which I'm going to talk today, is right on the emission component that comes only from the jet. So we don't have perturbations from emission from other components in the Aegeans, like for example here in the optical, infrared, sometimes UV, where you have a component of emission from the accretion disk or even from the dusty torus. Right? So in principle, when you observe in the millimeter range, you observe only the jet, right? The same happens also for the gamma ray regime. Okay. So properties of the millimeter emission of these kind of objects, they are usually very highly variable, much more than actually in the radio domain. So in the the higher you go in frequency, usually the more prominent it is the variability. And this kind of, I mean, here you have an example of the same source that I was showing before, where you have this very prominent flares at 3 millimeter and 1 millimeter. Actually, this is data taken from our monitoring program here at IRAM. And they can reach variability, let's say, differences by up to an order of magnitude in time scales of months to days, up to days. We know that this variability is most of the times connected causally, by the ejection of fast superluminal features, as those that you have seen in the previous movie of OJ287. So whenever you have a very sharp and prominent flare in the millimeter regime, you are almost sure that a new superluminal feature is being ejected from the inner regions of the jet. Okay, this is another example. You see actually the different multispectral range actually here in red and blue millimeter emission and light curves actually of this source. 0235 plus 178 is another very well-known BLAC object, another blazar. And here, right, this yellow mark, actually it's marking the time when this strong superluminal feature was ejected from the jet. So, I mean, there are very many examples of this kind of behavior, and we are now sure that whenever there is a very prominent flare, there is an ejection in the jet. Okay, actually, this kind of studies actually started to give an idea that actually the picture that we have to take in mind when studying blazars is this one, where the millimeter emission region is located at progressively upstream jet regions when you move to higher frequencies, right? And actually we know now, because of other different studies, that this actually millimeter emission region is located at about 1 to 10 parsecs from the center engine, from the center black hole, right? Okay, so this is the current toy model or paradigm of a blazar. Here you have the central black hole, the accretion disk that can emit in the optical to ultraviolet, and then extending farther out is the dusty torus that emits mainly in infrared. Here is the location where the X-ray corona is placed. It's thought to be close to the central black hole, but the geometry of this corona is actually not well known so far. And then we actually have the evidence to know that there is some kind of clumpy medium that we call the broadline region, and then farther out in the jet, the narrowline region that emits, of course, spectral lines. And then in the way from the central engine to the region where we thought that it is, and that these jets are emitting more prominently in the short millimeter range, there is the region of acceleration of the flow that we thought it is threaded by helical magnetic field that confine the jet and actually help to push the jet up to relativistic speed so that they can emit later out. Also, actually, in the main millimeter emission region, it is thought that we have what it is called a recollimation structure, which is formed actually because of pressure balances between the external medium and the jet. So the jet initially, of course, has some pressure. It starts to expand at some point, but there is a distance or a point where the external medium starts to push, and when that happens, then the the jet reconfines again, and then it creates a standing shock, which is ideally a stationary shock. So this is being a shock. It is a region of pressure and density enhancement, and this is one of the regions which where it is thought to be located the core or the region of prominent emission in the millimeter range. But we also have the possibility, and actually this is something that it's coherent with the observations that we have of shock wave, plane perpendicular shock wave propagating farther out the jet, where you also have pressure enhancement, particle acceleration, and prominent emission. So essentially, in millimeter relativistic jets are a combination of a smooth jet with a recollimation shock and then also shock waves propagating and moving there. Okay, so this is the picture from which we depart. And up to now I have been talking about what we know. Here is what we still don't know about Aegean jets. So some of the main questions are why some Aegean jets why some Aegean forms jets and why others not. Actually, there is a majority of Aegean that do not form jets. Those with jets are a minority, but it is actually not. It's an enigma still. What is the mechanism why some of them form jets or not? We are starting to understand, but not completely, how jets are formed from the central engine. And actually, definitely, it's a big problem to know what keeps them collimated up to hundreds of kiloparsecs. This is actually one of the, I would say, oldest problems in jet physics in Aegeans. What is the composition of the plasma of the jet? We still don't know if they are composed by electron-positron pairs or electron-proton. And the difference, because of the different mass of the positron and the proton, is actually more than significant by a factor of about 2,000, and that influences actually all the energetic backjet of jets, on which regards to what is the influence of the jet in the external medium, deformation, emission mechanisms that actually are related to another very relevant problems regarding active galactic nuclei. So the influence, what it is called the jet feedback for the influence of the jet on the evolution of the intragalactic and intergalactic medium, also in clusters and so on. No? And actually the emission mechanism in jets that I have been talking about before. Okay, so to understand all these problems, which are not only actually blazar or jet relativistic jet problems in Aegeans, but in general Aegean problems of Aegean science, it is critical, of course, to know the properties of jets. It's clear that knowing the composition, how jets are formed and so on, you would know about general problems about, like this one, for example. So this is a motivation to study jets, and actually doing it in the millimeter range has a lot of advantages, mainly because, well, not very many studies have been performed before. I would say that almost no studies in the millimeter range of blazar jets have been done before, and also because the millimeter range has some properties that allow to see a non-distorted view of jets that I'm going to explain later. But first of all, and this is where the second part of my talk is starting, about the Polemy project, I wanted to stop here to acknowledge the collaboration of all this large team of contributors to the project, some of them here in the audience. If you want to get more information after my talk about the program, you can go to the webpage polami.iaa.es, and there, well, we are usually posting news about our project, last publications. We have information about contacts in case you wanted to have access to some particular data set or actually, of course, the composition of our team. And we will be updating the webpage so that we include new stuff eventually. Okay, so what is Polami? Polami, I repeat again, this is the polarimetric monitoring of Aegeans at millimeter wavelengths. And it's a long-term monitoring of the 4 Stokes parameters of a set of Aegeans, not only blazars actually, we also have radio galaxies and yeah, mainly blazars and radio galaxies. We perform this monitoring with the export polarimeter that was developed by my good friend Clemens Thum here in the audience. And we use for that the IRAM 30 meters telescope, which is located here at about 30 kilometers from here in the Sierra Nevada mountains. This is a nice white telescope that most of you people who observe in the optical in the observatory of Sierra Nevada see in front of you, and it produces so nice pictures of the sunsets from there, actually. But it is more than that. Actually, this is, besides, the telescope has, I think it's more than 30 years old also. Not very many people know that this telescope has been, and I don't know actually if it is one of the most productive, scientifically speaking, telescopes in the world at ground, without counting space missions. And it is also for the millimeter range standards, one of the biggest surfaces, so that gives us a lot of sensitivity which is needed to observe polarization, because actually when the sources that we observe are usually not highly polarized, the maximum is usually up to 10–15%, so you reduce by 15% the emission that you want to study, and you need good sensitivity. So, good properties of or advantages of studying blazar emission in the millimeter range is that we know from previous studies that this emission is not highly affected by Faraday rotation of the polarization angle, and this is an effect that can produce also what it is called Faraday depolarization, which doesn't give you an actual intrinsic idea of what is the polarization of your source. So if you don't have large Faraday rotation and you don't have Faraday depolarization, you are studying the intrinsic properties of your sources. And actually at millimeter wavelengths, we know from really long time ago, from lots of studies, that we are not affected by opacity effects in the total flux, and also on the polarization effect, in the polarization emission. So that means, again, that when we observe in the millimeter range these kind of objects, we are free of, let's say, effects that distort or be. We still have, of course, the relativistic aberration, but we cannot get rid of that. And we also know, I have already mentioned before from previous VLBI imaging studies, that the millimeter emission, that the short millimeter emission is very compact and concentrated at the beginning of the jet, what it is usually called the core in VLBI observations, so that, I repeat again, studying these objects, these highly anisotropic jetted objects with a single dish telescope is still a good approximation to the total flux and polarimetric properties of these jets, because the emission from these jets at the millimeter range is very, very compact. Okay, so this is actually a list of the sources that we have been monitoring for many years since the beginning of our program. We have been monitoring others, but with second priority. So we have also performed a couple of very big surveys of hundreds of sources, but these are the sources that we have been monitoring more intensively to produce this kind of light curves here in total flux. They are a total of about 40 gamma ray bright sources that are also being monitored very intensively in the optical with polarimetry, with a set of more than 10 telescopes in a collaboration that we also participate from the Calar Alto telescope and also from the Liverpool telescope. And they are also being monitored with VLBI at 7 millimeters, so that we have, of course, there is plenty of gamma ray data of these sources because they are being observed in the whole sky survey, Fermi, and very frequently also in the X-rays. So there is a plethora of data sets of all these sources in all spectral ranges, so you can perform very detailed multispectral range studies of them. So we selected actually these sources because there was already established very comprehensive monitoring programs at other spectral ranges and with many different techniques. Here I'm showing a plot of the kind of data that I'm going to show during the rest of the talk. You will see typically at the total flux, linear polarization degree, linear polarization angle, and even circular polarization in red at 3 millimeters and blue at 1 millimeter. For our monitoring, we intended to have a time sampling of about 2 weeks that we have never reached with any of our sources, mainly because you have weather problems with your observations. Not all sources are visible at the time of the time range of your observations, but this is essentially our goal. We have some sources that approach that goal, but not all of them. So the kind of results that I'm going to show in the next slides correspond to the compilation of data that we did from 2006 to 2014. And the analysis of this data is contained in this set of 3 papers that were submitted and published actually as a single pack to monthly notices of the Royal Astronomical Society. That was our intention. We tried to publish everything together, but then in the process of production, actually, the journal screwed everything up, and they published actually our second paper first, then the third paper in the same number of the journal, and 2 months later our first paper. There is actually, we were asking for a correction of this, and the journal couldn't do it, but they actually have published an errata and they are apologizing for that actually, but the damage is already done. Anyhow, this is what I'm going to talk about, but the scientific production of Polamin is not only this, because we actually participate we are rather collaborative and open, and we share our data with anyone who is interested to make any multispectral range work of any of our sources. And actually there is already something, I think it was the last month I was counting something like 30 papers more, where our Polamin data has been used, or we actually used them together with other spectral range data from other spectral ranges to make a multispectral range studies of sources. The good news is that we are still monitoring. So we still follow our sources, and this is actually an updated data set of one very well-known quasar, where the last point shown here was taken actually, I think it was 1 week before or something like that. We are now in a position of having a very fast data calibration, so we update our evolution cubes essentially after every one of the observations. Okay, I start here with the results that we have gotten from our data. First of all, regarding total flux. Here I'm showing for this source, 0827, this is total flux at 3 millimeters, total flux at 1 millimeter, and this is a spectral index, which is the logarithm of the coefficient of the total flux at one and another. There is a criterion usually in radio astronomy to call positive spectral index, where you are in the spectrum in the optically thick region, and negative spectral index is when you are in the optically thin region of the spectrum, which is not affected by opacity. So actually what we see in our data, this is actually one of the few counterexamples, is that most of the spectral index is optically thin, not affected by opacity, right? Only in very, very prominent flares, and not only in all of them. Actually, here you have an example of a prominent flare that doesn't reach optically thick spectral index. Only in very exceptional cases we have huge opacity effects, but mainly all of our data is exempt from those opacity effects that would imply complications in the interpretation of the data. Right? Okay, regarding the linear polarization degree, here in this second plot, as I said before, in blue, remember, you have 2 millimeter linear polarization degree. In red is in blue is 1 millimeter polarization degree. In red is 3 millimeter polarization degree. So the first thing that you see from this plot is that the blue points are always, in general or in average, higher than the red points. That means higher linear polarization degree at 1 millimeter than at 3 millimeters. And this is not a single example, it's actually something general that happens also in this source, and in general in all our sources. So from the analysis of actually more than 2,000 measurements from our about 40 sources, we have reached the robust conclusion that there is a factor of about, an average factor of about 2.6 larger linear polarization at 1 millimeter than at 3 millimeters. And since we are not affected by strong Faraday effects, we can assure that this is produced because the average magnetic field is better ordered on the shorter wavelength regions as compared to the longer wavelength ones. This thing about the order is explained because if you have very well ordered magnetic field, actually you will, in principle, have to obtain the theoretical polarization degree from synchrotron emission, which is about 75% or so. So the reason why you usually observe less polarization degree is because you have other regions with different polarization that compensate, cancellate orthogonally, and that reduces the polarization degree. So the larger the volumes that you have, or the less order actually the polarization emission region that you have, the lower the polarization. So this is why this conclusion is gotten. Okay, variability of linear polarization degree. We also see actually, if you take a look here again, that there is a lot of variability, that the polarization degree actually, well, this is, you have seen that this is a time range of about 8 years. You see that the polarization degree at both 3 millimeters and 1 millimeter varies a lot, and that they vary in a range from 0 degrees to 15 degrees. You have something similar here in this second example. This is OJ287, also a well-known blazar by lots of us. And we also see, actually, not only that there is a huge variability, but also that this variability is actually more prominent in polarization degree than in total flux. This can be explained by an argument similar to the one that I was saying before. In principle, when you have total flux, you have different regions of total flux. All of them contribute to the integrated total flux of the source. So the more regions that you have in total flux, the more emission. No? If you have a polarization emission and the many different regions that you have different polarization orientations, then the orthogonal cancellation of polarization makes them to cancellate at some point, and that if that system is dynamic, then that produces more variability in polarization than in total flux. Right? So this is the interpretation that we have in mind, and also the fact that we have also been taking from the data that the time scale of variability at shorter wavelength is more significant than at lower wavelengths is consistent also with the shorter wavelength emission coming from smaller regions. So if they are smaller and they are competing in polarization, then you should see more regions, smaller, competing, more variability, right? Okay, now variability of linear polarization angle here in this plot. Remember, total flux, linear polarization degree, and linear polarization angle. We see from all our sources that all of them are variable in polarization angle as well. So this is another example. There are different modes of variability, but all of our sources are varying in some way, both at 3 millimeters and 1 millimeter. We have that about 60% of our sources show a rotation of more than 180 degrees in polarization during the course of our observations. And this rotation happens typically in time scales that go from a week to a year. Mainly, the average is about 1 month or so. And one of a very easy result that you can see actually from watching at the data, but there is also, of course, a formal study about that. I'm talking about a formal statistical study, is that the variability of the polarization angle of our sources, the polarization degree, and the total flux do not correlate at all. And this is something which is surprising, because in principle, if you would have a single emission region, you would expect that the total flux and polarization emission that are produced by the same mechanism, in this case, millimeter emission in synchrotron, would have a coherent evolution. But this is very far away from what we observe in all the sources. So that means that the emission cannot come from a single emission region. That means that there should be more than one. And because of the competition and cancellation of polarization, then there is not a coherent way of variability of the total flux with polarization, and also with polarization degree and angle. Right? So this is a very robust conclusion that it was more or less suspected before, but this is another proof about that. This excludes what they are called one-zone models, that they are very popular on interpreting the spectral energy distribution of these kind of sources. So if you want to take into account the polarization emission to take it into account, you cannot use simple, actually they are usually spherical models. People usually model a jet as a sphere. We actually know it's logical to know that this is not a good approximation, but this is actually a robust proof about that. Okay, the relation of the linear polarization angle of our sources with the jet position angle. There are theories, mainly for axisymmetric jets, that predict a particular observed polarization angle of jet sources, depending either on their geometries and also on the kind of observations you make. So that we know that if the jets are purely axisymmetric, and you integrate all the polarization emission from this source, you should observe them to show their polarization angle either parallel or perpendicular. Just because of the same argument that I have been telling before, because of cancellation of orthogonal polarizations in this axisymmetric geometry of a jet, right? So there is no way to obtain in an axisymmetric jet a polarization angle that it is that it is diagonal. So in this plot, in this histogram, actually, I'm showing the difference between the polarization angle of the more than 2,000 measurements that we have made for all our sources with regard to the jet position angle of every particular source where we measure this polarization angle. And well, here in red is for 3 millimeter data, in blue is for 1 millimeter data. Of course, we have less 1 millimeter data because it's the 1 millimeter data is more noisy, so we have ruled out about half of the data, actually. And essentially what we have here is that 0 means linear polarization angle parallel to the jet position angle, and 90 degrees is perpendicular, right? And what we see is that the histogram is more or less evenly distributed between 0 and 90. That means that the linear polarization degree do not have a strong preference for either aligning either parallel or perpendicular to the jet axis. There is perhaps a little bit of excess here for sources having a soft trend to show their linear polarization angle close to the jet position angle, but these are a minority, actually about 20% of the sources. In general, what we see is actually sources are evenly distributed, and since we know that for axisymmetric jets, we should see all the sources either here, perpendicular, or here, parallel, and what we see is actually the other way around. The main conclusion is that this model is not valid. So, and this is another very robust conclusion, that it is also well known from before, but this is an alternative, a new confirmation that blazar jets are not axisymmetric, as also many people use for making their models of jets. So if you want to take into account polarization emission, which is very much constraining with regard to total flux, mainly because it removes several degrees of freedom on the kind of models that you can take into account. You cannot, in general, I mean, there are particular cases where you can use axisymmetric models for your source if you want to reproduce with high fidelity your source. And then I'm coming here almost to the end of the talk, but here is where I'm going to show the more, perhaps the newer part of the work that we have been doing. We'll finish in a couple of minutes, but let me go in a little bit of detail with this plot. So, circular polarization. We, for the first time, have been making a deep monitoring of the circular polarization of these kind of objects in the millimeter range. So essentially nothing was known before about circular polarization, and we are starting to understand or to characterize what is going on in these sources regarding circular polarization. So here in these two plots, I'm showing the circular polarization, the histograms of the circular polarization measurements from our secured and polarized calibrators, which are Mars and Uranus, that are almost point-like for the telescope, and so that they are guaranteed to be unpolarized. You see that these distributions are actually centered on 0.0, actually, and they have a Gaussian profile that corresponds to systematic uncertainties, right? So actually the width, at least at 3 millimeters, the width of this Gaussian actually is the uncertainty that we know that we have for many reasons on our measurements, like weather instabilities, instrument instabilities, and all these kind of things, no? And any other factors that may influence in some uncertainty in a measurement. So this is actually after computing the errors for every one of the measurements of our targets, we added an additional 0.3% to our data. So every one of these measurements actually has a 0.3% measurement error at least. So what we see actually from the comparison of the calibrators that are centered at 0, non-polarized, and our targets, like this one, for example, these are the distribution of a small sample of our targets, is that blazars show absolutely different emission profiles on these histograms. They have from very broad distributions as compared to the calibrators, to sometimes significantly shifted to 0, double peaked like here, and several detections up to 2% by more than 5 sigma. Circular polarization is also detected in all but one of our sources, and most of the times it is detected more than once in a single source. And there is also, actually, and this is very relevant, a number of sources that we have detected. When we have detected a source, most of those detections for every particular source are always on the same sign. One of the messages I wanted to leave here is that circular polarization is routinely detected at millimeter wavelengths. This is new, and even more, the circular polarization that it is detected is of the similar level and magnitude, let's say, than the one that was reported before at centimeter wavelengths. So that is the last thing that I was mentioning is important, because it's talking about it's providing information about how to model the source, and it's giving information about what is the origin of this circular polarization emission. So regarding the variability, what we see is that there is faster circular polarization. In this plot I'm showing total flux, linear polarization, and circular polarization at 3 millimeters only, where we have better signal to noise for a particular source. And what we see is that the circular polarization is more variable than linear polarization. It varies in time scales of months, and perhaps sometimes in time scales of weeks. And we have frequent sign changes from positive to negative, and then positive in essentially all the sources that we have observed. So the time variability and circular polarization sign changes point to some level of small-scale inhomogeneities of a smaller scale as the linear polarization that we have been here. So here's a remark about the possible origins of Faraday of the circular polarization. We consider Faraday conversion or intrinsic circular polarization, but I think this is not for this audience. Essentially, I mean, these are the possibilities, but we are still not sure about which mechanism on every particular source. For that, we need modeling, and that is the next step on which we are working, actually. Okay, a summary of what I have been talking before. These are essentially a collection of the main messages that I have been showing during the talk, that I'm not going to repeat here. Actually, I have to stop essentially now. But let me just give you a very short message. We are now, with the data that we have here, in a position to start making modeling of the full polarization spectra of blazar jets in the millimeter range, in combination also with simultaneous data in the centimeter range. And this is going to open a new window for precise measurement of the parameters of the jet. So as I was mentioning before, linear polarization is removing some degrees of freedom on jet models with regard to total flux only, but if you also add circular polarization, you are constraining much more the kind of parameters of the jet and models that can apply. So we are at the beginning of a new window for high precision modeling of modeling of blazar jets and their parameters. And I will finish with this conclusion from the results that we have gotten from these first 3 Polami papers, is that we can actually modify slightly this standard picture of jets, only slightly, because as we have seen during the talk, in order to take into account polarization, emission and variability at millimeter wavelengths, you cannot have actually only axisymmetric jets. You need, even if it's a small level of non-axisymmetry, and together with that, you need more than 1 emission regions, perhaps more than 2 or 3 to account also for the fast variability that we see on both linear polarization and circular polarization. Thank you very much. Sorry for the delay.
Ivan, questions, please?
Thank you, Ivan, for this nice talk. I have 2 questions. One of these is about the spatial scale of the region, you know, with some kind of coherence in the emission, in the polarization emission. All right, you say that you see that you know, they are smaller as your resolution or you know, your precision in the measurement of polarization emission is better. But do you have upper limit for this the size of this region?
Not yet. I can make some guesses, but that will need some confirmation. Actually, we are. I mean, our next wave of studies that we are already planning, and actually we are working on that, includes, together with comparison of the variability of emission in gamma rays, optical polarimetry to be compared with our data. We are also actually doing a comparison of the VLVI ultra-high resolution images in polarization of our sources with the single dish long-term variability of the sources, and this will give us about which region is producing which rotation or variability, and we can actually measure the actual size of these components. So the answer is we still don't know, but from the variability, actually, we know that the variability, at least on linear polarization, have time scales of about a month or so. Sometimes they can be smaller. So if we take into account that these sources are relativistic, their speed are more or less the speed of light, so the size of the regions should be similar to the time scale of variability because of causality arguments. So that means about a month light, a week light, roughly speaking.
More questions?
Hi. I was wondering if you have rotation measure values for your sources, or if you can get this information from your data.
It's evident that you are a polarization guy as well. That's why you are asking for that. We did it. We made a test, and actually in our paper we included a study of the rotation measure on which we could do. But we had two problems. Mainly that we were measuring only in two wavelengths. 2 wavebands. So you know that when you try to make the rotation measurement between 2 wavelengths, then you have an ambiguity by produced by the pi ambiguity in the polarization angle. So that was not very much helpful, but still we tried to at least put some constraints on what would be the minimum levels of rotation measure that one could measure by try to align the linear polarization angle at 3 millimeter and 1 millimeter, and from that we computed estimated non-secured actually rotation measured. And what the conclusion that we got is that the rotation measure in that in these sources can be as high as 10 to the 4, 10 to the 5 radians per square meter. But this is only soft statement. Actually, we cannot guarantee that there are no higher or even, of course, lower, because this range, actually 10 to the 5, 10 to the 4, is within the range of our errors on measurements of minimum rotation measures.
So the next question is this enough to depolarize with Faraday, the polarization at 3 millimeters more than 1 millimeter?
Not in our spectral range. If you have 10 to the 4, 10 to the 5, that implies a change in polarization angle at 3 millimeters by 10, 15 degrees at most. So 10, 15 degrees is not enough. So for producing the polarization, you need to rotate by 90 degrees so that you have cancellation of different polarization emission components. And 10, 20 degrees is a very, very tiny depolarization.
You mentioned that you need, in order to interpret the data, that there is more than one zone in the emission. Okay, do you have any hint also of the possibility of having spine sheath structures in all the sources, and whether it gets an influence in the results you get in the polarization or not?
Yeah, that is certainly a possibility, but we can, from our data themselves, we cannot infer anything regarding to that. We know that there should be this at least a small level of non-axis symmetry. Even if you have a spine sheath model for your jet, it is allowed to have some level of non-axis symmetry, and this is compatible with our model. But the spine sheath model by itself do not tell you if the polarization angle should be parallel or perpendicular if you account for emission from both components.
What I was thinking is the sheath should have a defined orientation, but the spine itself not, while it evolves due to opacity reasons or to the presence of different zones, as you have mentioned, and then they can in a certain way compensate the one to the other and produce some variability also. I don't know.
Of course, that happens. As you say, it's true that the sheath has a very well known orientation of polarization angle, but since you don't know about the other component, it can have shocks on it, and it should have actually as well. And they have been seen in some sources presenting spine sheath and so on. In principle, unless you go to this study that I was mentioning to Emilio that we are starting to do now of comparing the single dish data with the ultra high resolution VLVI data, there is not much to say about that.
Thank you, Ivan, for the talk. I have learned many things, but the most, I am questioning totally from outside the field, is this huge majority of AGNs which do not have jets. And there is 90%. So why all of them have a disk, and probably this activity and these bursts are due to instabilities in the disk, but I just ask whether you have general differences of jetted AGNs and non-jetted ones. Morphology of the galaxy, total luminosity, total mass, and also physical properties, polarization or whatever.
So I'm going to tell you what I know, which is only a very little. So, there are experts actually on this kind of studies. What the picture that I have in my mind from what I have heard in different conferences that I have is that there are many factors that can influence on what is on what produces a powerful jet that can emit and be observed from cosmological distances, actually, because most of these sources are at high redshifts, at least much more than one. So in the jet formation process, it looks like the magnetic field is a very relevant component. The structure of the accretion disk is a relevant component, and very probably, of course, the spin of the black hole. So there are models that try to explain the formation or non formation of efficient jets, mainly by spin of the black hole. There are models where the accretion disk is counter-rotating with regard to the black hole, and these are scenarios that do not favor the formation of very powerful jets and so on. The magnitude of the magnetic field, which is an essential ingredient on the formation of the jets, may be playing a very key role on there, but the truth is that there are no conclusions about what is the reason. So there are some hints, but no real conclusions about what is producing this dichotomy. That's my picture. Perhaps somebody here in the room knows a little bit more than me.
General differences, for instance, redshift or total luminosity or mass of the host galaxy, these kind of things.
So you need a lot of material falling into the black hole, and then depending on the accretion and how the magnetic field is arranged, you have a magnetically arrested disk, or which are efficiently
the spin of the black hole as well, and so in general, I think everything is interrelated. There is no.
It's in the high accretor AGNs are basically radio quiet or not jetted. Why? I don't know. Well, my question is, where are produced the flares that provoking the variability? In the jet or in the accretion disk?
That's another very nice open question.
My question is because I am not sure, because I don't know if there is a relation between the variability that we observe in the optical and also in the UV and the variability in the radio range. So because if the flare it's coming from the accretion disk, then it's affecting of course the VLR, and if there is a relation with the radio, we know where is producing the flare. But I don't know.
You are observed. If it's jet dominated, like what they are classically called radio loud objects, most of the emission, both in the optical and UV, is dominated by the jet. So you should see a correlation between what it happens in the radio band and the optical UV bands. If they are not, then most of the emission comes from the disk of this optical UV emission. But in that case, you don't have a jet, so you do not see the connection. We know some things about what is the connection. I mean, to answering this question about where are these blobs produced that are being propagated in the jet. So for sure that they should be related to the accretion process and the jet formation process, of course. So that should be that should come mainly from the accretion disk. And actually, there are some hints and some nice work that point to that. And actually, there is a very nice example of actually the favorite source of Jose Luis. There was it a Nature paper, the one by Ellen, where there is, this study lies specifically on this particular topic of the connection between the jet and the accretion disk. So in this case of 3C120, it was seen that the X-ray emission of this source, actually 3C120 is a very particular source because it has properties of a blazar but also a radio galaxy. So it's not pointing directly to you, but at some larger angle, so you are able to see the disk in X-rays, but the radio emission is dominated, of course, by the jet. No? And in this case, it was observed by a very dense monitoring that there was a lot of variability in the X-rays, and this variability was coherent with the radio emission and also with the ejection of blobs. And it was observed that whenever there was a dip in the X-rays, that means that the accretion disk is removed out, at least the innermost one that is emitting most prominently, either accretion disk or the closer regions in the center engine. Whenever there was a dip, there was a few, I don't know if it was days or weeks, months later, there was an ejection of a component. So there is a causal relation between you are removing a bit of the disk, you are processing all this material, you drag something on the black hole, and the remaining material is ejected in the form of a shock wave in the jet. Mm-hmm.